They will not be here today. Okay. All right. Welcome back. Let's see. So we're back. We're in person. It's exciting. Logistical nonsense. So I did post this page finally. I kind of put together all the stuff I've been writing about the exams and stuff. So the sort of gradient philosophy, the logistics. Here is, I finally made a page about nicely written solutions. And I have a compilation just to give you a sense, the kind of things I'm looking for. You know, you can look at this. These are stuff, I wrote some really these are all for integral calculus. I wrote some over the top solutions for some integrals. And then these are some solutions that students turned in last semester. So you can sort of see just how nice things can be if you really take some time and try to write out your thoughts and notice how much English is in these solutions. That's a good thing. People are writing words. It's amazing. Words can be used in math. Shocking, but I think you know, a lot of the questions from the midterm were sort of short answer-ish, and I don't think you have to write full pages for everyone. You know, like if I go back to let's see, I put the exam here, just if you want a clean PDF. You know, I think almost everyone in the class got this one right. The x equals 7. So there's not a ton to explain there, you know, but you can still write a few sentences being like, and some people did on the exam. Some people just wrote the answer x equals 7. Some people wrote, oh, okay, well, it's parallel to the YZ plane. The YZ plane is x equals 0. That means this plane is x equals constant. It passes through this point. So x has to equal 7. You know, you can write a sentence or two. It doesn't have to be an essay on every problem, especially since a lot of these are sort of short. Okay. But then especially for like the last one, like I definitely, people again on the test wrote more on these problems anyways, because they're sort of conceptual problems. So, but yeah, and I am almost ready. I'm almost ready to publish the responses. I'm like on number 5. My other class was a little more needy, my integral calculus class, so I finished theirs first over the weekend, and I'm almost done with yours now. So I should be able to get the feedback, but you can go ahead and start, you know, writing your solutions. And they'll be due Friday, but I will also give you the weekend grace period like I do for problem sets. So you do have some time. Okay. Cool. Any questions about any of that? One thing I didn't talk about that much is that you do have to write a self-assessment also. And again, this doesn't have to be super long or anything, but you know, I kind of want you to tell me how you felt the closed book version went. And then like, you know, also who you talked to and stuff, like resources. And maybe just like a little bit about the course and just your learning in the course, just to see where you are. It's nice to read those and see where students feel like they are at this point in the semester. Okay. And then also another thing, I don't know if I sent this to you last week, and I had it at a 0 to 5 point scale. And I did that for my other class, and I published the solutions. And then the thing is, like, every problem's worth 5 points, so you got like a total score. And I was pretty harsh. I like wouldn't give out 5 out of 5 a lot of times. I would like be like, oh, you need to write it, you know, for your final version, you need to write more. So I'll give you 4 out of 5 for this. So the scores were low, and students were freaking out because they were looking at their total score, which is something I never intended for the students to look at, like, because it ended up being a score out of 60, and like the median was like 38 out of 60 or something. And so people were emailing, freaking out, like, oh my God, I've totally bombed this exam. And I'm like, no. The point of the closed book thing was just like a first attempt. It's not worth very much of the grade. That number doesn't mean anything. That sum, I just was giving everything on the scale of 0 to 5. So for you guys, so I switched back. I actually just made each problem worth 1 point on grade scope, and I just switched to like a check system, check plus, check minus, check. Because I don't want you to think of that as a number that's like actually represents like an actual Like if you got a 38 out of 60, that does not mean you got like 63% on the test or something, right? Like if I gave every problem with 5 points, you know what I'm saying? Anyways, so I felt bad that I did that to my other class because I think I demoralized like half the class over the weekend. That was fun. Good job, Emmy. All right. So anyways, so these are the kind of responses you'll see when I publish the grading. So, okay. Anything else? Okay. Yeah, sorry, this has all been a longer process and everything than I intended. The last few weeks have obviously been non-standard. So, okay. Maybe we should do some math. So if we go to the handouts page, let's see, there's still this this critical points PDF, and we never looked at the last problem. We talked about critical points and classifying critical points, finding and classifying critical points. The second section of the chapter, 15.2, is more about like, how do you argue something is an actual like global max or min, maybe, you know? And I will assign some problems like that. So I want to kind of go through this problem and talk about it a little bit. Let me go to the Blackboard though. So pull this up if you, I mean, it'll be on screen here in the classroom, but okay, so let me pin myself also. Okay, let me make sure the board is visible. All right, okay, so I like this kind of problem. We're actually gonna solve this problem like 7 different ways, because I think it's interesting and illustrates a lot of concepts of multivariable calculus. But one of the first ways we can solve it is as a typical, just finding the max and min of a function of 2 variables. Even though there's 3 variables involved at first, because, well, look what the problem says. It says find the points on a certain plane, find the point or points which are closest to the origin, right? So find the point on x plus 2y plus 2z equals 18, which is closest to the origin. And so closest to the origin means we're going to find a point whose distance from the origin is smallest, right? So the distance from x, y, z to 0, 0, 0, we all know is the square root of x squared plus y squared plus z squared. So that's what we want to minimize, right? We're going to minimize that function. But we're only minimizing it for points on the plane, right? I mean, obviously we want to minimize the function without constraints. 0, 0, 0 minimizes this function, but 0, 0, 0 doesn't land on that plane. So I think, so the first thing I say is convince yourself that it is just as good to minimize the square of the distance. Do you believe that if you minimize the square of the distance and you also minimize the distance? If the minimal square of the distance is 9, and the minimal distance is 3. Yeah, so it's just as good to minimize x squared plus y squared plus z squared. There's sort of an official reason, which is that the square root function is monotonic, is the word, that it's always increasing. If I wanted to be sort of formal about this, because the square root of, I'll just say u, is monotonic. So it's sort of, this means always going up. right? If we drew the graph of square root function, it's like this. And so if you minimize, if you find a minimal height on this curve, then it's also going to be a minimal y value on this curve will correspond to a minimal x value, right? If I say like, oh, the lowest point I can get to is this height, then that means it also minimizes the x, and it's because the function is always going up. If it went up and then back down, that might not be true. That makes sense? Okay, I think it makes sense probably intuitively, and then there's sort of a mathematical justification, fancy terminology that people like to use. Okay, now this is a function of three variables, which we haven't really talked about. I mean, we could still find critical points, but again, the issue is that there's this, we want to incorporate the plane somehow, right? So you could make this a function of two variables. X is 18 minus 2y minus 2z. So that implies that we really are looking at the function of y and z given by, I just plug in for x. So that's a function of two variables that we want to minimize. Does that make sense? So now we're using the constraint that like it's not all x, y, z, it's only x, y, and z satisfying this equation. Okay, so I guess that's part B on the screen. Find the critical point. Well, you guys can do that. Maybe you should just do that at your seats for a few minutes. Set the partials equal to 0. I don't think you need to FOIL this out. You could probably do it by just chain rule differentiation. You could FOIL it out if you really want to. But set the partials equal to 0, find the partials set them equal to 0. Try to find y and z. You know, work with your neighbors, compare notes. I'll walk around. Used to being back in the classroom. Normally I would hover over students and make them uncomfortable, but this might be extra discomfort because I just had COVID. Unintended discomfort. Yeah, there's a little bit of work you have to do here because it's, you know, for two equations and two variables, right? Oh, you're writing words. I like words. All right, I'll start. I'll be behind you guys, but I'll start. Is that what the chain rule says? 2 blah times the derivative of the inside. So you end up with this extra minus 2, right? I think the first equation, is that what you guys got? First equation? Something like that. Is 18 times 472? I think so. All right, so f sub z should be very similar. So this is exactly the same thing, but with 10z. Okay. There's almost a sense in which simplifying this actually makes life a little bit harder. Because what can you really conclude from these two equations? Y equals z, right? I mean, because that's what's going to end up happening. And you can almost see it better from these because these are equal to each other, but these terms are the same. So they could cancel from both sides and you get 2y equals 2z, right? But let's see, if you did write it out like this, then that means, right, 10y plus 8z is 72, which is 8y plus 10z. And then everything cancels from both sides except the 2y equals 2z. Y equals z. And then you can plug back into either equation and get y. So then that means, for example, we plug back in here, we get 10y plus 8y. (72), 18y is 72, so y is 4, and z is 4. Is that right? What you got? Good. Okay, so that's just algebra at that point. Now, we can also, plug this back into the original plane equation to get what x is. But I did ask this question first of like, we found a critical point, but we haven't classified it. We could still classify it and show that it's a local minimum. Maybe we should do that. Good practice from our second derivative test, right? So let's see. So let's classify this just to make sure. I mean, it's a minimum, and then we can argue why it's a global minimum, not just a local minimum. All right. So again, you can get ahead of me a little bit if you want. So classify. We could actually almost even skip this and still argue why it has to be a global minimum, but doesn't hurt to practice this. So, okay, we need the second order partials, right? So I think if I look up there, FYY is just 10 because you're getting up with 10y plus 8z minus 72. Is that right? FYZ is 8. Same logic. Coefficient of the z in the partial y, or the coefficient of the y in the partial z. And FZZ is also 10. Sort of interesting. They're just constants. So D, remember, was this funky expression, which here happens to be 100 minus 64, which is greater than 0. Remember, when the discriminant is greater than 0, yeah, this should be in your notes. then you actually get a max or min. So it's only when the discriminant's negative that we get a saddle. And FYY or FCZ are positive, which I think I was trying to indicate. I felt like it was hard to do over Zoom because I was drawing in the air, that at least in the y direction, the function's concave up, right? Meaning y, saying the second y is 0 means that it's concave up. If you just did a like x equals constant slice to that point, that'd be like the second derivative being positive, so it's concave up. But if it's a local max or min and it's concave up in some direction, that means it's a min, right? Because it has to be either all concave up no matter which way you slice it, or all concave down no matter which way you slice it. Okay, so implies local min. Okay, so that's good. So that's what the second derivative test says. Why is it a global min? I think you have to be a little, you have to think about this a little bit. It's kind of, again, what I like, if you, I'm not going to spend a ton of time talking about section 15.2, but they do give some arguments. When you want to argue that a local minimum is actually a global minimum, because we're trying to find the minimum value, right? And I guess the issue here is that, remember what the function was. The function was it 18 minus 2y minus 2z squared plus y squared plus z squared, right? We found one critical point that was a local minimum. So you might think, well, that just automatically means global minimum, right? If there's only one critical point in local minimum, then that means global minimum. And maybe for functions of one variable, that's true. Because if I want it to go back down, like you could argue, okay, well, maybe it goes back down and actually isn't a global minimum. But why wouldn't this happen for a function of one variable? Yeah, these would also be critical points. So you would find more critical points, right? So for a function of one variable, I think if you have a local min and it's the only critical point, then you can argue that's a global min, or else you would see other critical points. But for functions of two variables, it's more dicey. Maybe something happens in a weird way where it sort of like curves around and back down without actually ever having a max or min sort of thing. I don't know. Like maybe it goes off to infinity in another one, some direction, off to negative infinity in some other direction and curls, but then somehow does it. It's harder to picture, but it's somehow maybe you got a lot more space to work with. So maybe there's some fancy way that it would turn out to not have another critical point, but still manage to turn itself downwards. You know, so, but I will say this. It is the only critical point. And if it was going to go down, basically it would have to go to like negative infinity, right? Because like if we have any minimums, they're found by finding the critical points. So this, oh yeah, sorry, thank you. I'm so used to writing f of x comma y. Thank you. Right, it's function of y and z. So it's only not a global min if f of y comma z goes to negative infinity for some sort of like y and z getting large. Right, if there was some way maybe that it happened to, like I said, do some weird dance and like avoid having a critical point, but still going down, which is just a little bit hard to sort of prove that that doesn't happen. Then because if it was not a global min, it would have to be, any other minimum would be found as a critical point, right? So it'd have to go to minus infinity in some direction. But what happens to this function as y and z get large? Yeah, it's always positive, right? We have a sum of squares, but f is a sum of squares. In fact, it does represent a distance, right? Is a sum of squares. It does represent a distance. So it's never negative. And in fact, as y and z get large, so you go to get large, implies f also gets large. Right, like if there had been like a cube here or something, then it might be harder to tell because y cubed, if y is negative, then y cubed is large negative or something. But because everything's just squared, everything gets big. And it should make sense in terms of the distance also, right? Like if you pick points really far away from, like if I pick points with x, y, and z on that plane, but really far away, the distance is going to be large, right? So, right, so that's kind of an argument. And you'll see other arguments, like there are some nice ones in the book, some examples in the book, where some functions only defined for like x and y positive. So you're kind of in the first quadrant. But then you can show that as you approach the boundaries, it goes to infinity, or as x and y get large, it goes to infinity. And so you're, so that's kind of what you're doing usually. Is you're really sort of seeing, well, if we only have this one critical point, what happens in the in behavior? And if the in behavior is predictable, then we can tell whether or not we have a global minimum or not. That makes sense? Okay. So this is a global min. And in fact, though, I should actually find the point. I never found, I found y and z equals 4, but also y equals z equals 4 implies x is 18 minus 2y minus 2z, which I think now is 2. Yeah. So the point 2, 4, 4 is closest to the origin. Okay. Fair enough. All right, any questions about any of that? All right. Now the next topic I wanted to talk about actually avoids this global issue. It's called constrained optimization. This is the other big type of optimization problem we can do, or like finding maxes mins kind of thing we can do. So constrained optimization. All right, so let's revisit. Well, actually, let me give you an example. So in fact, let me download this this first, one of both of these notebooks. Actually, let me go ahead and download both of them. Okay. So let me give you an example, and then I want to talk about the down a dimension case, because that's what we always do in multivariable calculus. Go back to somewhere we know. So example. Find the max and min value of the function x times y, our good old saddle. But with the constraint that, with the constraint x squared plus xy plus y squared is less than or equal to 3. Seems kind of random, but I have a function and a constraint. Okay, and you can see, if I go to Mathematica, let me make this bigger. Yeah, I mean, here's the function x times y. This is a contour plot, right? The function x times y, it gets bigger as you go in the northeast and southwest directions and gets smaller as you go in the other two directions. And here's the curve. This is a tilted ellipse, actually. And so I'm only thinking about points like inside that ellipse. And now that becomes a sort of a different type of problem, right? So yeah, let me draw this. So here's here's something that's just not obvious, right? So now all of a sudden we have a region of the plane. We're focused on a specific region of the plane. So it looks like we have something like see if I can draw something like this. Oh, I messed up by drawing the axes first. That's a terrible looking ellipse. Okay, so good enough. So this potato is the function, is the constraint, the points satisfying x squared plus xy plus y squared less or equal to 3. Okay. And so it's like you want to think about evaluating the function xy on every single point in here and on the boundary and asking for what's the maximum number you'd get and the minimum number you'd get. Right. So we do this back in functions of one variable. So let's go back to functions of one variable for a second. So back to y equals f of x. If we have some function, like that, something like that. But now we put the constraint. Well, the constraint here is usually like an interval, right? And if I say, well, let's go over this interval from A to B. Okay. So y equals f of x. With the constraint, A less than or equal to x less than or equal to B. Okay. So we can look at this example and identify the max and min points, right? But if you remember, where can the max and min points occur in this kind of example? Like, what do you have to check? The critical points and the endpoints, right? So it's not just, so the critical points are still important, although this one falls outside the interval, so I'm not caring about it. So you find the critical points within the interval. So these are the places the max and min can occur. They can occur these 3 points, but they can also occur here or here, right? And in fact, I guess this ends up being the min, and this ends up being the max. So the max and min values occur either at critical points within the constraint, within the interval, or at endpoints of the interval. right? So that's a constrained optimization problem of a function of one variable. That's how that would work. But here now, like you said, we have this weird. In fact, you can start to look at if you overlay the. Now we have this region, this elliptical region, and we're overlaying it with this contour plot. It's a little bit weirder now, except let's think about the analog. The analog to at critical points or on the endpoints is going to be still at critical points. Like if this was a bowl shape, if this was a bowl and we constrained to this tilted ellipse, the minimum would still be at the bottom of the bowl, right? So that could be at a critical point still. But it could also be on the boundary. And that all of a sudden becomes a slightly harder problem. Like how do you find maxes and mins on an actual boundary curve? Here it's nice, there's the dimension small enough that the boundary is just 2 points. It's just the endpoints. So you get a finite number of points to check. But now all of a sudden our boundary here is much more complicated. So that's going to be the real issue, is like, how do we do that? So, right, so back to z equals f of x comma y, subject to the constraint. Let me just sort of do it in general. The constraint is going to be another thing like g of x comma y is less than or equal to c. That's kind of what we have in our example, right? And our example is x squared plus xy plus y squared less than or equal to, what did I say, 3? Right? So the maximum values can occur either at one, at critical points, or 2, on the boundary. Here I should say critical points within the constraint. Right, if it's outside the constraint, you would just throw it away. Because it wouldn't be, the critical point wouldn't be relevant. Okay, so this, this first one's easy enough. We've sort of been doing this for a while. But this one is the one that's like, uh-oh, this is a brand new problem. Okay, so this is a brand new problem, is like, how on earth? I can't just plug in all infinitely many points on the boundary curve and try to figure out where the max and min are. Wait, I'll get both of these. Does that mean I can do either? Yeah, okay. So it's kind of fun to try to look at this and sort of see what this actually looks like. So, the rainbow circle of death. Hello. Make this bigger. All right, so here is the surface, right? And actually here is it with the, like, from above, there's your constraint. And then but it looks on the surface, it looks like this thing, if you can see that. Okay. And so you can actually look at this and sort of, I try to identify where the max and min points are, right? There's like these two ends over here that seem to be the minimum heights. And then maybe these 2 points here that are like the maximum heights, right? And it's kind of nifty. You can get some neat pictures if you think about this stuff now. It's almost like I'd like to just erase the rest of the surface and just have this like weird lozenge or mouth guard or something. It's like, give me a mouth guard. I don't know. Does that make sense? Okay, so, but I think actually in terms of the picture, in terms of actually trying to figure out how to solve a problem like this picture is more useful. So let's see if we can figure this out before the end of class. So again, you can eyeball the points, right, where the max and mins occur, right? It seems like the max is like here and here maybe, because the highest point you get to is 1. But then the lowest z value is this -3 right here. So again, you can almost eyeball this and say, okay, probably the maximum value is 1, and the minimum value is -3. But in general, if I didn't have this nice picture to look at, how would I find these points, right? So in our example, sorry, let me stop the share. In our example, we have f of x comma y equals x times y, and we have this constraint curve, x squared plus xy plus y squared equals 3. Okay. But here's the thing, I'm actually giving this as a function because I want to think of this as the level curve of a function. This is like a level curve of g. Right? And now we can start to use some of the stuff we've developed, some of the sophisticated ideas we've developed. You see that kind of, right? Like what, I don't know, what jumps out to you about what's happening at those points? If we're thinking of both of these as like, the red is a contour, right? The red itself is a contour of, it's one contour of this function g. And then the gray line, the black lines or whatever are the contours of the other one. And what sort of happens at the points where the maxes and mins occur? They intercept. Yeah, like it's interesting, right? So they do intersect, but that's actually only because I drew this perfectly, because there's lots of contours here. But at this point right here, like on the bottom right, for example, the contour is, they're kind of tangent to each other. They're kind of like parallel momentarily at that moment, at that point, right? Whereas at these other points, the red curve is actually crossing contours of the function. Can you argue why that makes sense? Like why this max or min wouldn't happen at a point where you're crossing, where the red curve is crossing a contour? Sarah? Yeah, right. So Sarah said if you like start here and you follow this red curve a little bit, then if you're crossing a contour, that means you're either going up or down, right? Because the only way you don't go up and down is if you follow a contour. So any of these other points where you're crossing a contour, this cannot be a max or min because one side is higher and one side's lower. Good. Okay. So that gives us, let me write that down. It gives us some sense of something that's going on here and maybe something to start to work with mathematically. So, yeah. Now there could be some weird things happening, like the curve could be passing through a max or min of the function and, you know, like a critical point of the function, and there could be some sort of ridge on the function where it's like going up on both sides. So you'd have to be a little bit careful, but it turns out the math we're going to develop is going to take into account all those possibilities. So notice at the max and min points, G is tangent to contours of F. Because if crossing a contour, one side is higher and one side's lower, which is not a max even. Okay, so in fact, G and F are sort of, well, yeah, they're sort of parallel. Okay. Let me draw a representation of that. So we have like a contour of F right here. Let me just draw a couple contours of F. And we have our G, which is itself a contour. It's itself a level curve, right? So this is G. Oh, I should have said equals C. It's really the specific equation, right? Okay, and these are contours of F, level curves of F. All right, but when two things are parallel or tangent, here's what we started to train ourselves to think. If two like planes or lines are parallel, then their normal vectors are also parallel. Okay. So this curve has some, and it's the gradient, right? This has some gradient vector. Let's just call this point P. Then this is like the gradient of G at P. But also, if you think about gradients on this function, supposed to be perpendicular. Let's just say they're going that way. And so notice, I mean, we could also draw gradients at other points. Gradients of this kind of go that way. I actually thought I had this in this. Maybe I picked an old version of this. Yeah, I thought I had something where I drew all the gradients on here. Sorry. But you can sort of see, like at these points, the gradients are not parallel, right? But at this point, the gradient is. So, i.e., we're looking for points P where the gradient of F is parallel at P, is parallel to the gradient of G. And now I claim that's enough information to solve this problem. So in our example, the gradient of F is actually y comma x, because it was x times y. And the gradient of G, it was x squared plus xy plus y squared. So that's 2x plus y comma x plus 2y. And now here's where the algebra gets to be a little bit funky. We're going to set the two things parallel. Two vectors parallel means one's a multiple of another. So, so we want, for example, the gradient of G to be lambda times the gradient of F for some lambda. Sadly, I think we're going to run out of time right in the middle of this computation, which is not ideal. But right, so remember, that's the way we decide if two vectors are parallel. If one's a multiple, this is a scalar multiple. Lambda. And so you get some equations that look a little bit unpleasant at first, but it's enough. I claim it's enough. So because what we do is we write down, so we write this down. We have 2x plus y comma x plus 2y is lambda times y comma x. And so that really means 2x plus y is lambda y, and x plus 2y is lambda x. And we have the constraint x squared plus xy plus y squared equals 3. And if you look at this, this is 3 equations in 3 variables, x, y, and lambda. Three variables, x, y, lambda, and then you want to solve. And it looks a little bit bad, but you can do things like I'll just say, maybe we'll save this, or maybe you can do this for yourself for Wednesday, because this is where we'll pick up. But you could, for example, divide the y over here and the x over here, and then you have lambda equals 2x plus y over y, but lambda also equals x plus 2y over x. Set those equal to each other, start reducing. I think you can actually see that x has to be plus or minus y pretty easily, which ends up leading to those points. But we'll do that on Wednesday. Sorry, I ran out of time right in the middle. But this method is called Lagrange multipliers. And that's what the lambda is for, Lagrange. And we'll actually solve and see this. And then I'll have a bunch of examples for you guys to work on in groups. Okay. Sorry, we didn't quite. For your own, you should feel this categorical imperative to go and solve this and actually find those points for Wednesday's class. But all right. Have a good one. Thank you, everyone. Good to see you all in person. Yes, thank you.